So far, we got to see if things are strictly neutral, acidic, or basic as a salt solution, right? Well, now they're going to jazz it up a bit. And now we have to rely on the acidity based on our Ka and Kb value, which is going to be the dissociation of acid and the dissociation of base constants. Okay, folks? And so a lot of times with these type of problems or this type of information, you will be given those Ka and Kb values so that you can compare them to figure out if it's going to be more acidic with the larger Ka or more basic with the larger Kb. So if you have a cation that is a weak acid and an anion that is a weak base, then the acidity or basicity is going to depend on the Ka and Kb values. And that cation can also be a conjugate acid, which we saw before, and the anion can also be a conjugate base, or they simply can be a weak acid and weak base. One example would be our NH4CN, okay? And this is going to dissociate into NH4 plus and Cn minus, both of which are going to be potentially acidic or basic and react with water. So NH4 plus is going to act acidic because it is going to be the conjugate acid of the weak base, NH3. So that definitely counts as the cation here. The Cn minus is going to be more basic because it is the conjugate base of the weak acid, HCN, which go ahead and allows us to check this out. So in order to figure out which one is more, if this solution of NH4CN is more acidic or basic, we would have to gather the Ka and Kb values of that conjugate acid and conjugate base here and go ahead and compare it. So we have a Ka value for NH4 plus is going to be, and really is going to be the Ka value for NH3, right? It's 5.7 times 10 to the negative 10 versus the Kb value of HCN, just associated into Cn minus, is going to be 1.6 times 10 to the negative 5. So as you can see, this solution is going to be more basic because of that Cn minus as a conjugate base. And also because the Kb value is larger. What can we do to verify that it's going to be acidic or basic? We can take our conjugate acid here and our conjugate base and do one thing. Mix it with water and see what's produced. So we have NH4 plus mixed with water, going to be in equilibrium to produce the weak base, and of course H3O plus. This is what causes acidity. Okay. Then we're going to have our Cn minus. Take this off. Our Cn minus here, and that's going to also be mixed with water to be in equilibrium to form HCN, which is our weak acid, and of course OH minus. This is what's going to cause basicity. So it's all about having those Ka and Kb values, being able to, of course, understand which one is a conjugate acid or base or simply a weak acid or base, and then break down those ions that way. So again, acidity is going to depend on the Ka and Kb value. And guess what, folks? If we want to figure out the acidity of an amphiprotic anion, for example, we still would have to get the Ka and the Kp values of the respective dissociated acid and dissociated base. So if you have the cation of a strong base, which we know automatically is not going to have any reaction, and then the anion from a polyprotic acid, then the acidity is going to depend on Ka and Kb, and you must compare and contrast. So what is the anion of a polyprotic acid? First, it's going to be amphiprotic, meaning it has the ability to donate a proton or accept one. And it has to have one or more ionizable protons, okay? So in its formula, it has to have the ability to donate one proton or more, okay, folks? So here's an example salt, Na2HPO4. So this Na2HPO4 is going to dissociate into two Na plus ions and an HPO4 2 minus ion. And that is the anion in question that has the ability to act as an acid or act as a base. So let's go ahead and see what that does in these couple of equations here. So we have HPO4 2 minus that we're going to start with, and we're going to mix it with water. When we mix it with water, of course, this has the ability to, again, donate a proton and produce our H3O plus, right? And so that is when HPO4 2 minus is acting as an acid. The HPO4 2 minus can also be mixed with water and accept a proton and form H2PO4 minus. And of course, also OH in solution. If it forms OH in solution, it has the ability to be basic. Therefore, you need to go ahead and compare and contrast the Ka value and the Kb value to figure out whether or not this HPO4 2 minus is going to be acting as an acid and be acidic, or acting as a base and be basic. So this time, the Ka value of when it's acting as an acid is 4.2 times 10 to the negative 13. That's given. That's awesome. But in order to find the Kb value, we have to bring back another expression, which is going to be Kw is equal to Kb times Ka. And so we can use Kw divided by Ka to find the Kb value. So I'm going to take 1.0 times 10 to the negative 14 divided by 4.2 times 10 to the negative 13. And what I get is 1.6 times 10 to the negative 7. And so what I have to do now is consolidate. Compare and contrast my Ka and my Kb value. As you can see, my Kb value is way bigger than my Ka value. So overall, if I have to figure out whether or not this solution here, this HPO42 minus is going to act as an acid or a base for this one particular, it's going to be basic, okay? So I would just simply say that this whole thing is going to be basic here. So it's a little bit more layering of details than what we saw before. But again, if you kind of organize yourselves, have note cards and flashcards or whatever you want to call them for yourself to help you recall this, then you will be okay with this information. And I did want to specifically write this out. Kb is greater than Ka, and therefore the solution is basic. So I want to have like a clear area of written that out. All right, let's move on. Okay, folks, so we've kind of gotten all the extents of what we will see as far as salt solutions and figuring out if they're neutral, acidic, or basic. This table simply displays acid-base behavior of various types of salts. They give a bunch of examples. They give different pHs, for example. If something is going to be basic, we have the cation of a strong base. Anion of a weak acid potentially can give you that. If it's neutral, you have a cation of a strong base, anion of a strong acid. And so this table can be helpful for students who like to see everything summarized, and also can be helpful when it comes to your overall flashcards. So again, I would simply just write a line if I'm going through, cross, just so I can kind of like break everything apart. And then each line in between, I will kind of figure that out and break it apart as well. And we know with all of our polyprotic portions, they can be acidic or basic based on Ka and our Kb values. Let's go ahead and get into an example by layering all this information together. So we're back at the Avengers compound. We know the drill. We're going to read the question. We're going to gather information, start talking to ourselves. That's the goal. So determine whether the aqueous solutions of the following salt are acidic, basic, or neutral at 25 degrees Celsius, okay? So we have a zinc formate, which is ZnHCOO2. They gave us a Ka of Zn2+. They gave us a Kb of HCOO minus, okay? And that's going to be helpful because we know we have to get the cation and anion to help us understand whether or not something's going to be acidic, basic, or neutral. And then for letter B, we have potassium hydrogen sulfide, KHSO3, and they gave us the Ka of HSO3 minus. So let's go ahead and get into some examples. First, for letter A, we're going to get all of our ions, and then for letter B, we'll go ahead and get all of our ions. So for letter A, we have ZnHCOO2. If we go ahead and dissociate into its respective ions, we're going to get Zn2+ and HCOO minus. So this Zn2+ is quite small for zinc, and it is more charged. It is highly charged. So we can say that it provides some type of acidity, while as this HCOO minus is going to be a base, usually a conjugate base, so it's going to provide some type of basicity. Now they already gave us the Ka value here, and that's going to be 1 times 10 to the negative 9, and they gave us the Kb value here, which is 5.6 times 10 to the negative 11. So for this one, it's a little bit easier for us to say, okay, all we have to do, since we have a weakly acidic and weakly basic coming together, we have to compare and contrast the Ka and Kb values. Which one is larger and which one is smaller? So as you can see, this one is going to be larger, so our Ka value is larger than our Kb value, so this solution will be considered acidic. If they're the same, then of course they'll be neutral. Let's go on to letter B. Letter B is going to dissociate to K plus and HSO3 minus. Now we know K plus is going to have no reaction because it comes from the strong base KOH. What about HSO3 minus? The only example we've ever had was HSO3 minus Phoenix. And HSO3 minus Phoenix came from H2SO3 Jean Grey. And so what does that mean and what does that signify? Dun, 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 polyprotic acid, folks. And so with a polyprotic acid, I don't know if this HSO3 minus is going to behave as an acid or it's going to behave as a base. So I have to go ahead and write my reactions as an acid and as a base and get my Ka and my Kb values. Now, as you can see, they did give me a Ka value here, but they did not give me a Kb value. So let me go ahead and write these reactions. Okay, so if HSO3 minus is going to act as an acid, then when it mixes with water, it's going to produce SO3 2 minus super Phoenix, right? And of course, H3O plus, which signifies that it's going to be acidic. All right, and then of course, if HSO3 minus of course, Phoenix acts as a base. It's going to be mixed with water. It's going to form H2SO3, which is that weak acid, and then it's going to form OH minus, which is going to be related to basicity, right? Now, they already gave me the Ka value. That was given. Now, I have to use my Ka value to find my Kb value, okay? And then I'll compare them. So my Kb is going to equal to Kw divided by my Ka. So that's 1.0 times 10 to the negative 14 divided by 6.5 times 10 to the negative 8. And what I get is 7.1 times 10 to the negative 13. And so which one is going to be bigger here? Let's see. Get another color. All right, we have 6.5 times 10 to the negative 8, and we have 7.1 times 10 to the negative 13. So therefore, my Ka value is larger than my Kb value, and this solution is going to be acidic. So now that we've gotten to a couple of examples, you want to be able to layer the information with any type of salt that you are given. All right, let's move on to the next thing.